Yes, yeah. So thank you very much for the introduction. My name is Kokkalis. I'm a first-year PhD student at the University of Edinburgh, and I'm excited to be presenting today our recent work on the computation of equilibrium in discrete first price auctions. And this is joint work with my amazing collaborators, so my supervisor, Aris Filos-Ratsikas, Giannakopoulos from the University of Glasgow, and Alexandros Hollender from the University of Oxford. And I want to start this talk by giving an example from my recent experience in Edinburgh, actually. And to my experience, I think there's only two certainties about life in Edinburgh during the summer. So first of all, I cannot change the slide. No. Yeah. So first of all, you're definitely going to come across the Fringe Festival, which is a huge festival takes place in August. And second of all, this rise in popularity of the city and everything makes it impossible to find accommodation in August, which is something that I'm struggling with at the moment. So I want to use the second part to motivate my talk about first price auctions. And I want to consider the case where we have four interested parties in getting a place for a month. So we can imagine us all of them having some value, which we can think of as the maximum amount of money that they would be willing to spend to rent this place. And as is actually the case in Scotland, these properties are being auctioned at the first price. So essentially, if you are the highest bidder, you will pay whatever you bid and win the item. So if we start by thinking what will happen if everyone actually bid their true value, in this case, Aris would be the winner of the auction, and he would pay £1,400 as expected. But then after seeing what everyone else bid in the auction, maybe he'll see that, well, I'll be better off just marginally bidding higher than the second highest bidder. So say £1,101 to still get the item but pay less. And obviously maybe he'll think about paying even less than that, and then there's some probability that he loses. So there is this strategic environment which is worth studying as a game. And more specifically, so from my point of view, when I'm trying to participate in this auction, I only know my value, right? So how much I value the item. And I don't know what the others are going to bid or the value, but I might have some prior belief about this. So maybe I think that Alexandros not having a place in Scotland would value this much more than the others. And at the same time, Aris might have his own beliefs about the auction. So maybe things that Yiannis would be more interested to join the festival, and maybe things that his student would be much better off in Greece for the summer. And then, so does everyone else. So everyone could have their own beliefs based on maybe some asymmetry in the information. So this is the model that we're studying. And to formalize this a little bit, so we have a set of n bidders that participate in the auction. We have a value space in the bidding space. The value space could be either continuous or discrete. The bidding space basically could be discrete, maybe has a multiple of some currency. And then we have a pure strategy that for each player, which maps their value to a bid that they choose to play in the auction. So then we study this well-known notion of an ex post utility, which essentially says that after we see all the bids of the players in the auction, we allocate to the highest bidder. So the utility is positive if bidder I is one of the highest bidders. And they get this difference between the value that they had for the item and the bid they chose. And notice here that we also multiply this. We scale this by this factor that counts how many bidders were tied for first place in the auction. So this is called the uniform tie breaking rule, and it's what's usually used in these cases. And as I mentioned earlier, there are these beliefs that bidders have about others in the auction and help them choose their strategy. So in most of our work, we focus on this idea of a subjective belief, which means that each bidder I believes that the value of a bidder J comes from some distribution Fij, and this can be different from any bidder to any other from different perspectives, etc. But it's also worth studying more specific models. So a model of interest is the case of independent private values, also called common priors, in which case the value of any bidder in the auction is the same from the perspective of from any other bidder. And even more specifically, there's a case where all of these distributions are the same. So the values of the bidders are IID from some distribution F. So then knowing these, having a way to model these values, we define the expected utility of a bidder I, which is essentially the objectives that they're trying to maximize in the auction. So given some possible bid that they can play and the strategies of the others, this is just an expectation of the ex post utility I defined earlier over the values of the others, drawn from the perspective of bidder I. And this clearly introduces the game of incomplete information. So we're, as usually, interested in stable states of these games, where people do not have incentive to deviate from their current strategy. So the solution concept that we're studying is the Bayes-Nash equilibrium, and I have a brief reminder here about what it is. So essentially what this says is that we're given a set of strategies, one for each player, and given that set of strategies, no player has an incentive to change the strategy to get a higher utility. And in fact, we are considering epsilon approximate equilibria, which says that no player can get an epsilon increase in their utility by deviating to another strategy. And the reason to do this is because maybe there are some cases in our work where maybe all the equilibria that exist are irrational. So for representation issues, it makes sense to allow this slack of epsilon in some cases here there. And as always, there are multiple interesting questions on the side of these equilibria. So first of all, does such an equilibrium always exist? And for the case where the prior distributions of the values are continuous, there's a well-known result from the seminal work of Arthur back in 2001 that says that existence is guaranteed under some wild assumptions. But then from the point of view of computational complexity, we're very much interested in would we be able to compute this efficiently? And this problem was put forth by Filos-Ratsikas et al. Back in EC'21 actually, where they introduced a computational study of it, and they showed PPD completed results in the case where we have subjective priors, which are also continuous. And for anyone not familiar for PPD, I'll come back to this later, but essentially you can view it as a strong evidence of computational intractability for now. And then there was very much a very interesting work by Chen and Peng in 2023, who proved another PPD completeness result for the case where the priors are common, but that they're somewhat different and a bit more involved tie-breaking rule. So this summarizes essentially the prior work. And as one of the main questions in the field is the setting of common priors, what we tend to do is, because it's easier to prove Hollender's results in the more general case, we do this. And then we also try to approach the problem from the more specific case and try to prove some positive results there. But all previous literature focused on the case of continuous priors. And as you guessed by my title, we will be focusing about on discrete distributions, which are also very well motivated because of representation issues in a computer, for example, that runs instructions. So just to reintroduce our setting a little bit, we have, as I mentioned earlier, discrete bitting space. We have discrete prior distributions, which are also subjective. And these new discrete distributions now mean that the arguments back in Arthur's work do not apply anymore. So existence of equilibria is not guaranteed. And in fact, there is this nice paper from 2009 that shows a counterexample of this. So then, just because we're studying this discrete setting, as I mentioned earlier, which somehow makes the presentation a bit, I guess, more intuitive as well. A question that comes up is, could the problem be easier in general in this setting? And here's an outline of our results. So we prove an NP completeness of deciding the existence of a pure equilibrium in our setting. And this naturally motivates the study of mixed equilibria, and for which we prove a PPD completeness result. And finally, we accompany those with positive results. So we provide a p-test in the case where the prior beliefs are IID. And I want to start with a brief outline of our first result, the NP completeness one. So in this case, actually not even NP membership is trivial. And this is because in computing a bidder's expected utility, there is this idea of quantifying over the values that the others can have. So this, if we just naively write down the expression, this is not efficiently computable. But we do present a dynamic programming algorithm that does that and can then verify certificates. So this puts the problem in NP. And for the NP harness, we provide the reduction from the circuit satisfiability problem. So then, as natural, this harness result for pure equilibria motivates study of mixed strategies and mixed equilibria. So mixed strategy now, what it does, it takes again a value, but instead of a single bit, it produces a distribution over the bit space that says with what probability the bidder played this bit in the auction in that strategy. And the appropriate solution concept now is the approximate mixed space as equilibrium. And this introduction of mixed strategies, in a sense, that they restore the continuity of the problem. So the existence of a mixed equilibrium can now be proved via standard arguments. So this makes the problem a total search problem, where we aren't guaranteed that there is a solution. We're looking to compute one. And yeah, as I said earlier, from the point of view of computational complexity, we're interested in what's the complexity of this problem, what would be the appropriate complexity class that captures its complexity. And could PPD be a candidate for this, for example? And here I'll provide a reminder about what PPD is. So in general, this is a class of total search problems where the existence of a solution is guaranteed due to some parity argument of directed graphs. And this has been able to capture the complexity of many key problems in our area, such as computing mass equilibria in general games and others. And as I mentioned earlier, there is this prior work by Filos-Ratsikas that studied the continuous case, continuous prior setting. But now here we have a mixed strategy in the discrete setting. So an idea could be maybe somehow establish a connection between these two settings. And the answer is yes. So we provide a nice equivalence result, actually, where starting from a discrete first production and given some parameter delta, we saw how to construct these continuous distributions now. So the blue lines right here represent the original discrete distribution. And we build these blocks of with delta around them to introduce a continuous distribution and hence a continuous reduction. And we show that with this reduction and mapping the strategies appropriately, we can move from any epsilon pure equilibrium in the continuous setting back to an epsilon plus delta mixed equilibrium with so pure equilibrium in the continuous setting back to an epsilon plus delta mixed equilibrium in the discrete setting. And we also prove the other direction. So given a continuous first production this time and a parameter delta in 0, 1, we now saw how to, in a sense, discretize these continuous distributions, and again, get a resulting discrete first production, for which we can map any epsilon mixed equilibrium back into an epsilon plus delta pure equilibrium of the continuous auction. And these two results are key to our PPT complete results. So first of all, for the PPT membership, we can use the first direction where we map a discrete auction to a continuous one, because then the problem of computing an equilibrium in the continuous setting is already in PPT. So this directly gives us the PPT membership. And then actually for the PPT harness, we could use the other direction of the problem, but as you saw in the previous slide, there was a slight asterisk in the mixed equilibrium of the discrete setting. And that's because there are some further properties there. So instead, what we do to make our result as general as we can, we provide the direct reduction from the PPT complete problem view circuit. And this is the updated state of the world now. So we have provided the first hardness result in the discrete prior setting. But again, the question remains what's the complexity of the common prior? So it makes sense, as I said earlier, to approach this from the more specific case and try to prove some positive results there. And that's exactly what we do next. So we consider the IID setting, where the beliefs about other breeders, they all come from a common distribution F. And now the appropriate solution concept is a symmetric mixed equilibrium, which means that all players play the same strategy. And this symmetry obviously makes sense because of this symmetry in the information that they have about the other breeders. And we, as I mentioned earlier, we provide a pretest for this problem, which we can think of as an algorithm that can achieve an epsilon approximation for any epsilon we want to pick, but with a polynomial time to the inputs of the problem, but perhaps exponential time in this IPR state that we're trying to achieve. And we prove that we demonstrate a pretest for our problem for computing a mixed equilibrium and a symmetric mixed equilibrium in the setting of IID priors. And here I want to also provide an outline of our proof. So first of all, to the best of our knowledge, there were no previous existing results for a symmetric and monotone equilibrium in this IID setting. So we do prove those using some standard fixed point theorems and some convergence theorems. And then there is a way to represent, a quite straightforward way actually, to represent the conditions of mixed equilibrium by just writing out a system of polynomial inequalities. And then we know that from a previous paper from Grigoriev and Vorobyev back in 1988, we know that we can use an algorithm as a black box, essentially, that achieves a solution that is delta near to a feasible one in polynomial time. So is that it? Are we done? Actually, no, because there is a caveat, and that's the description of this problem. So if we just naively again write out this system of inequalities, it will be exponential in the number of players, the size of the bidding space, and the size of the value space. So for our pretest, we try to get rid, in a sense, of all these exponential dependencies in these variables. So first of all, just because we are considering symmetric equilibria in the IID prior setting, as I mentioned earlier, the symmetry allows us to get rid of the exponential dependency of the number of players, because we only consider the game from the point of view from one strategy at a time. For the bidding space, we provide a lemma that shows that we can consider a shrunk bidding space of size big O 1 over epsilon. And then we can compute an equilibrium in that shrunk bidding space and translate it back in equilibrium with the resolution that is a good approximation. And finally, and perhaps most interestingly, we can use the monotonicity that we guaranteed in the very first step to succinctly represent the support of the strategies and then be able to enumerate over them. So this gets rid of the exponential dependency on the size of the value space. And as you see here in the second step, this is why we get a beta. So the tighter the approximation we want to achieve will pay a cost as we are we have an exponential cost on 1 over epsilon. So yeah, now we can finally use the algorithm I promised in the second step and achieve solutions delta near. But again, this might violate some of the constraints. So there's a simple last step that just rounds the solution back to a feasible one and bounds the approximation of this resulting equilibrium. So this is now the updated state of the world. So finally, we have a positive result in the IID prior setting. And the main open question remains what happens for common priors. And in fact, what happens both in the discrete setting that we've left open, but also, as I mentioned earlier, there is this result in the continuous setting, but this is for a specific tie-breaking rule. And would be very interested to see what happens when we consider one of the most common, perhaps, yeah, the most common uniform tie-breaking rule. And maybe because we've also tried to prove some PPT completeness result there, and it seems difficult, perhaps this could be lying somewhere further down in the hierarchy of total search problems. So that would be very interesting to explore. And in terms of positive results, there's actually a PITAS on the Chen and Pen paper from 2023, which is a PITAS, but it is for a different notion of a pure equilibrium. And we would be very interested to extend this to the definition that we provided for equilibrium, which is, again, I think the standard one. And there's multiple other questions that are worth studying, and that perhaps our equivalent result that I demonstrated earlier helps us think of problems in either the settings and translate results between the two. So I'm very happy to talk about all of these and any other question you might have offline. And thank you.